Welcome to qnawire.
Hi, so over here we have three different parts of a question. The first one is how many moles of sodium hydroxide we need to add to 1 liter of 1.6 molar solution of HC2H3O2 to produce a buffer solution at pH equal to pKa. So for this problem, we're given that the Ka is equal to 1.8 times 10 to the minus 5, which corresponds to a pKa, which is the minus logarithm of Ka, equal to 4.745. So in the first case, I'm going to abbreviate this directly as HA, just to exemplify that it is a weak acid. So in order to reach the equivalence point, we know that we need to have the same, in order to reach a pH equal to the pKa, we know that we need to reach a concentration of the weak acid to be equal to the concentration of A minus. So essentially, we're going to have C0. We need to add 1/2 of my initial concentration of my hydroxide. And this is going to produce the following ice table. Uh, Initial, change, and equilibrium. All of this in molarity because we have 1 liter and that's easy for us. So we would have at equilibrium C0 over 2, 0, and C0 over 2. Thus the concentrations are the same and the pH is equal to the pKa because our Henderson-Hasselbalch equation tells us that the pH of a buffer solution is equal to pKa plus logarithm of A minus over HA. So the amount of mole that we need to add is the initial amount over 2. If we initially have 1.6 moles of my weak acid, then I need to add 0.8 moles. Now let's see what happens in cases B and C. In both of the cases, what is going to happen is that the pH is going to be different than the pKa. So I'm going to write down the general procedure for both of them, and then we're going to substitute the values that we require. So for B and C, the procedure is going to be the following. We're going to have our weak acid plus OH minus that is going to produce A minus plus water. We're going to write down our ice table, and I'm going to write it down again in terms of concentrations. C0, we're going to add an X amount of OH minus, and we'll start with 0. Water doesn't matter because it doesn't enter into any equilibrium calculation. So the amount of change is going to be minus X, and X. At equilibrium, I'm going to have C0 minus X, 0, and X. So our Henderson-Hasselbalch equation is going to look like this. pH is equal to pKa plus logarithm of X coming from the concentration of A minus divided by C0 minus X. Now we need to solve for X, and the way to do it is the following. We're going to start by collecting pH minus pKa on the left-hand side over C0 minus X. Then we're going to leave it to take 10 as a basis. So we're going to have 10 to the pH minus pKa. And this will be equal to X over C0 minus X. Next step, I'm going to continue over here just to make the derivation not as lengthy. Next up, we're going to multiply by C0 minus X. So we're going to have C0 times 10 to the pH minus pKa minus X times 10 to the pH minus pKa, and this will be equal to X. Next step, we're going to collect all the terms with an x on the right hand side. So this becomes C0 10 to the pH minus pKa is equal to x plus 10 to the pH minus pKa times x. We're going to factorize over here the factor of x. We have 1 plus 10 to the pH minus pKa. And finally, with this, we know that the value for x that we need to add in order to reach the desired pH will be C0 10 to the pH minus pKa over 1 plus 10 to the pH minus pKa. And this is the equation that we're going to use for both of the problems B and C. So for B, my initial concentration is the same, 1.6 molar. This implies that we have 1.6 moles. Everything correct. We don't need to do any further calculation. And the desired pH is equal to 4. The pKa is the same as before, 4.745. Thus, pH minus pKa will be equal to minus 0.745. So far, so good. So the amount that I need to add will be 1.6 multiplied by 10 to the minus 0.745 divided by 1 plus 10 to the minus 0.745. The result is 0.244 mole. This is the amount that we need to add in part B. Now, in part C, the procedure is quite similar. My initial concentration, same thing, 1.6 molar. My desired pH is equal to 5, and pKa is the same, 4.745. So pH minus pKa now is going to be equal to 0.255. Now it is positive. So the amount that I need to add will be 1.6 multiplied by 10 to the 0.255 divided by 1 plus 10 to the 0.255, giving us a value of 1.03 mole. And that would be all. Thank you very much and have a good one.